There are galaxies in the sky that look older than the universe they are sitting inside, not slightly older. Old enough that, taken at face value, the light left them before there was anything for it to leave. You have almost certainly met some version of this claim by now, and you have probably met what it supposedly proves, that the beginning of everything did not happen the way you were told, that the calendar is broken, that somebody somewhere is not being straight with you. Tonight we are going to find out whether any of that holds up, and I'm going to give you a plain answer before we are done. But the whole thing turns on something almost nobody mentions. Nobody has ever put a galaxy on a scale. Not once, not ever, not anywhere. So what exactly have we been measuring all this time when we say how much something out there weighs? Settle in and let the room go quiet. Subscribe if you haven't already, and stay with us, because by the end of tonight you will know exactly what we got wrong, and it is not the thing the headlines picked. Let's begin. Part 1. The claim you have already heard. Somewhere in the last 2 or 3 years, you almost certainly ran into a version of this sentence. A telescope in orbit found galaxies that are older than the universe. The wording changes depending on where you met it. Sometimes it is a headline, sometimes a thumbnail, sometimes a comment underneath a video about something else entirely, written with enormous confidence by someone who is very sure that the people in charge are not telling you everything. But the shape is always the same. We looked further back than we had ever looked before, and what we found there could not possibly be there, and therefore the story we have been told about the beginning of everything is wrong. I want to be careful with you here, because that sentence is doing 2 completely different jobs at once, and only one of them is honest. The dishonest job is the obvious one. Nobody has found a galaxy older than the universe, not once. There is no object anywhere in any catalogue that has been shown to have existed before the cosmos that contains it. The claim, stated that baldly, is not a finding that scientists are quietly suppressing. It is a misreading of a real result, and it has been passed hand to hand so many times that the misreading has become the thing people remember. The honest job is much more interesting, and almost nobody talks about it, and it is the reason we are here tonight. Because underneath the bad version of the story there is a real problem. It is genuinely unresolved. It has been getting slowly worse for 20 years, and in January of this year, a group of astronomers working out of an observatory in the Netherlands published a measurement that made it worse again, in a way that almost no one saw coming, including the people who had spent a decade proposing the solution that the measurement quietly demolished. So let us start from the beginning, and let us start with the thing that makes any of this possible in the first place. Telescopes are time machines. That is not a metaphor, and it is not a flourish. Light moves at a fixed speed, and space is enormous, so light takes time to arrive. When you look at the moon, you're seeing it as it was a little over a second ago. When you look at the sun, you're seeing it as it was 8 minutes ago, which means that if the sun stopped shining right now, you would have 8 minutes of ordinary afternoon before you found out. When you look at the nearest star beyond our own, you are seeing light that left it a little over 4 years ago. And when you point a large enough instrument at a faint enough patch of empty-looking sky, and you hold it there for long enough, you start collecting light that has been travelling for so long that the universe was measurably different when it set out. The James Webb Space Telescope is the largest instrument we have ever put into space, and it is powerful enough that it has collected light from galaxies as they existed when the universe was a little over 2% of its current age. 2%. If you compress the whole history of the cosmos into a single human lifetime of 80 years, that light left home before the first birthday. It is worth pausing on how recently that became possible, because the frontier has moved absurdly fast. In 1998, the most distant galaxy anyone had confirmed sat at a redshift of 5.6, which is already an extraordinary thing to be able to say. By 2006, the record had crept up to just under 7. In 2016, it reached 10.6. Then the new telescope opened, and in 2 years the record went to 13.2, then to 14.18, and then, in 2025, to 14.44, a galaxy called MOMZ-14, whose light left it 283 million years after the beginning. That is the current record as of tonight. In the span of a single human career, we went from seeing the universe at roughly 1/10 of its present age to seeing it at 1/50th. And here is the thing about looking that far back. We know what we are supposed to see. That is the entire point of the exercise. We have a model of how structure grows out of a smooth beginning, and that model makes predictions about what the sky should look like at every stage, and those predictions are specific. At 2% of the current age, galaxies should be small. They should be blue, because they should be crammed with enormous hot short-lived stars burning through an abundance of raw material. They should be irregular and unfinished and busy. They should look, if you will allow the comparison, like hyperactive children. Some of them do. That part of the prediction came through beautifully, but mixed in among them, the telescope keeps finding something else. It finds galaxies that look grown up. Galaxies that look red and settled and finished, with the light signature of a stellar population that has already lived through its loud phase and come out the other side. Galaxies that appear to weigh far more than anything should have managed to accumulate in the time available. Not one of them, not a fluke. A steady trickle that has continued for 4 years and shows no sign of stopping. That is the real result, and the distance between that real result and the sentence you met on the internet is where the whole story lives. Now, before we go any further, I want to hand you the single most useful thing you will hear tonight, because everything that follows hangs off it, and once you have it, you will never read an astronomy headline the same way again. We have never weighed a galaxy. Not one. Not ever. There is no scale. There is no instrument anywhere on Earth or above it that has ever been placed under a galaxy and given a reading. What arrives at a telescope is light, and only light, and nothing else. Photons that left an object an unimaginable time ago, travelled through expanding space, and finally landed on a mirror. From those photons you can measure how much light arrives, and at which wavelengths, and with what fine structure written into it. Everything else, the distance, the size, the age, the mass, the number of stars, is not measured. It is calculated. It is inferred through a chain of steps, each of which depends on the step before it, and one of which depends on an assumption that a man wrote down in 1955 while looking at the stars in his own neighbourhood. Hold on to that. We are going to come back to it, and when we do, everything is going to look different. Because here is what makes this particular story worth 2 hours of a quiet evening. It would be very easy to tell you that the scientists are wrong and the model is broken, and the universe is secretly much older than they admit. That version is available everywhere, it is free, and it is not true. It would be almost as easy to tell you the opposite, that everything is fine, there is nothing to see, the anomaly has been explained, go to sleep. That version is also available, and it is also not quite true. What actually happened is stranger and better than either. Astronomers found a problem. They proposed an elegant solution, one that was physically motivated and genuinely beautiful, and for a few years it looked like the solution was going to hold. Then somebody went and measured the thing that the solution depended on, and the measurement came back pointing the wrong way. Not slightly wrong, backwards. The escape route turned out to lead further into the building. So over the next 2 hours we are going to do this properly. We are going to build the universe we expected to find, so that you can feel what a crack in it actually costs. We are going to look at the hard limit that makes the word impossible mean something specific rather than something dramatic. We are going to walk through the discoveries, and then through the corrections that quietly undid a lot of them, because the corrections are the part nobody covers, and they are the most instructive part of the whole affair. We are going to take apart the measurement chain, link by link, until you can see exactly where the softness is. We are going to look at the beautiful solution, and then at the January measurement that closed it. We will give the people who say the Big Bang is finished their strongest possible case, in their own words, and then we will see how it holds up. And at the end of all of it, we are going to answer the question in the title, plainly, without hedging. Because we have been wrong about something. That much is real, and I am not going to soften it. The question is what? Make yourself comfortable. Nothing in the next 2 hours requires you to stay awake for it, and if you drift off somewhere in the middle, you will not have missed the point, because the point is going to keep arriving in different forms all the way to the end. And the first form it takes is a question that sounds simple, and is not. What, exactly, were the first galaxies supposed to look like? Part 2. The Universe. We expected to find. To understand why anything about the early universe could be described as impossible, you have to understand how confident we had every right to be. This is not a case of scientists making a loose guess and then acting surprised. The prediction that got broken was one of the best supported predictions in the whole of physical science, and it was built on a foundation that had been checked more carefully than almost anything else we know. It starts with the oldest light there is, About 380,000 years after the beginning, the universe cooled just enough for electrons and protons to hold on to each other and form neutral hydrogen. Before that moment, the cosmos was an opaque fog of charged particles, and light could not travel any meaningful distance without being scattered. After it, space became transparent, and the light that was flying around at that instant was suddenly free to keep going. It has been going ever since. It is still arriving. We call it the cosmic microwave background, and it is by far the most precisely measured thing in cosmology. Here is what makes it useful. That light is almost perfectly smooth in every direction. Almost. If you measure it carefully enough, you find a faint dappling across the sky, regions that are very slightly hotter and very slightly cooler than their surroundings, by about 1 part in 100,000. Those variations are not noise. They are a map of where the matter was very slightly bunched up and where it was very slightly thinned out at the moment the universe became transparent. To put 1 part in 100,000 in perspective, if the surface of the ocean were that smooth, the largest wave anywhere on Earth would be about 4 inches high, and we did not measure that dappling once. We measured it 3 times, with 3 generations of instruments, each better than the last. A satellite called COBE found it in 1992 and won its team a Nobel Prize. A satellite called WMAP mapped it properly through the 2000s. Then a European satellite called Planck spent 4 years measuring it to a precision that is difficult to convey. It pinned the temperature of that ancient light at 2.72548 Kelvin, which is to say a little under 3 degrees above absolute zero, with an uncertainty in the 4th decimal place. That number is the single best measured quantity in cosmology, and it will matter again much later tonight, for reasons that will not become clear for about 90 minutes. Those tiny lumps are the seeds of everything. Every galaxy you have ever seen a picture of, every star, every planet, the atoms in your hands, all of it grew out of the fact that the early universe was not perfectly even, and gravity has no patience. Now, the crucial detail. The matter doing most of the bunching is not the matter you're made of. There is roughly 5.5 times more dark matter in the universe than ordinary matter, by mass. If you tally up the total matter budget, about 84% of it is dark and about 16% is the ordinary kind, the kind that makes hydrogen and carbon and iron and people. And dark matter has one enormously convenient property for anyone trying to model the early universe. It does not do anything complicated. It does not glow. It does not cool by radiating. It does not form molecules. It does not get blown around by exploding stars. It falls. That is essentially the whole of its behavior. It falls into its own gravity, and it pulls the ordinary gas in behind it. So the picture is this. Dark matter collapses first, forming enormous invisible structures we call halos. Think of them as gravitational bowls, spread out over regions far larger than the visible galaxy that will eventually sit in the middle of them. Gas pours into the bowls. The gas can do things dark matter cannot. It can radiate away heat, which means it can lose energy, which means it can fall further and get denser, and when it gets dense enough, it lights. The first stars form inside those bowls. They are made of hydrogen and helium and essentially nothing else, because nothing else exists yet. Every element heavier than lithium in the entire universe was manufactured later, inside stars, and thrown back out when those stars died. The iron in your blood was assembled in a stellar core and delivered by an explosion. That is not poetry, that is inventory. Those first stars, incidentally, were expected to be monsters. With no heavier elements around to help the gas shed heat, the clouds could not cool efficiently, and a cloud that cannot cool cannot fragment into small pieces. The early estimates put the first generation of stars at hundreds, even 1,000 times the mass of the Sun. Keep that idea somewhere safe. It is going to become the hinge of this entire episode, and the number has been quietly shrinking for 20 years. Then the small galaxies collide. They merge, and merge again, and the bowls merge with them, and over billions of years the structure builds upward, small to large, simple to complex, chaotic to settled. This is called hierarchical assembly, and it is the central claim of the standard model of structure formation. You do not start with big things and break them up. You start with small things and stack them. This is not a story about the distant past only. It is still happening, and we live inside the evidence. Our own galaxy carries the wreckage of at least one substantial collision from about 10 billion years ago, visible today as a population of stars moving on strange orbits that do not match anything else in the disk. Andromeda, the nearest large spiral, is inbound and will arrive in a few billion years. And the dark matter bowl our galaxy sits in is not a subtle thing. Its gravitational reach extends far beyond every star you can see, out to distances of hundreds of thousands of light years, holding satellite galaxies in orbit around a centre that, from their point of view, is mostly empty. And here is why everyone was so confident. Because the dark matter part of that story is the easy part. Modelling gas is a nightmare. Gas is turbulent and magnetized, and it cools in complicated ways depending on what elements are mixed into it. Stars explode inside it and blow it around. Black holes eat it and belch it back out. Radiation pushes on it. Any simulation of gas is a simulation of 100 competing processes, half of which are not fully understood, all of which have to be approximated. If someone tells you they have precisely predicted the behavior of gas in a young galaxy, be gently skeptical. But dark matter does not care about any of that. Dark matter feels gravity and, as far as anyone can tell, nothing else. Which means that predicting how dark matter halos grow over cosmic time is one of the cleanest calculations in the field. You take the pattern of lumps written into the oldest light, you apply gravity, you let it run, and you count what you get. The answer depends on the expansion history and the initial spectrum of lumpiness, both of which are measured to within about 1%. So the model made a specific and, in principle, difficult-to-dodge prediction. In the first billion years or so, the first 7% of cosmic history, there simply should not have been very many large halos. The bowls take time to grow, and no bowl means no galaxy, because there is nothing to hold the gas in place. That prediction is the wall this whole story is going to run into. Along with it came a prediction about what the galaxies inside those small early bowls would look like. They should be furiously making stars because the gas supply is enormous and untouched. They should therefore be dominated by the biggest, hottest stars, which are the ones that shine most fiercely in the short wavelengths, which means they should look blue, and they should stay blue for as long as the party continues, because the enormous stars that make a galaxy blue only live for a few million years, so you need a constant supply of new ones to keep the colour. The corollary matters as much as the rule. When a galaxy stops making new stars, it turns red, and it turns red fast. The blue giants die off within a few million years and are not replaced. What is left behind are the smaller, cooler, redder, far longer-lived stars. So redness, in a galaxy, is a clock. It says, this thing stopped. That is the picture we carried into the launch. A smooth beginning with a faint dappling. Dark matter collapsing into bowls, slowly, in a strict order, with big ones forbidden early. Gas falling in behind it. Small, blue, disorganized galaxies at the dawn, merging upward into the large ordered ones we live among now. Every step of it supported by measurements, most of it verified again and again against the sky at intermediate distances where we could already see clearly. And then we built a machine capable of checking the earliest part of it directly, for the first time, and we pointed it at the beginning. What came back did not fit. But before we look at what came back, we need to be precise about one word, because it is going to do an enormous amount of work for the rest of this, and almost everyone uses it loosely. What does it actually mean for a galaxy to be impossible? Part 3. The ceiling. The word impossible gets thrown around a lot in this field, usually by people who are not the ones doing the calculating, so I want to show you the version of it that has actual teeth, because it is not a vague statement about models being strained. It is a conservation law, and conservation laws are the closest thing physics has to a locked door. In 2022, an astronomer at the University of Texas at Austin named Michael Boylan Colchin wrote a very short paper, 4 pages, 2 figures, no co-authors, which he dedicated to the memory of Steven Weinberg. The published version appeared in Nature Astronomy the following year. The title of the preprint before it was polished for the journal was Ruling Out Lambda CDM with High Redshift Galaxies ? The question mark was his. That tells you a lot about the man's honesty, and about how carefully this argument was meant to be read. Here is his reasoning, and I want to walk it slowly because it is beautiful in its simplicity. At very early times, dark matter and ordinary matter were mixed together evenly. There was no mechanism to separate them and no time to do it. So when a dark matter bowl forms and starts pulling material in, the ordinary matter it captures is in the same proportion as the universe at large. That proportion is a measured number, ordinary matter accounts for about 15.5% of the total matter density. 15.5% everywhere as an inheritance, which means that any given bowl comes with a fixed allowance of ordinary matter. It cannot get more. There is nowhere for more to come from. That allowance is the absolute ceiling on how much stuff that halo can ever turn into stars. Not a soft ceiling, not a modelling assumption, but a statement about how much material physically exists inside the region. So astronomers write it as a single line. The stellar mass equals some efficiency, times the baryon fraction, times the halo mass. The efficiency is the fraction of a halo's entire allowance of ordinary matter that has been successfully converted into stars, and the efficiency cannot exceed 1, because 1 means you have used every single atom of hydrogen and helium the halo was ever given, with none left over, none blown away, none still floating around as gas, none locked in dust. 1 means perfect. What makes this argument so much stronger than an ordinary galaxy formation calculation is that it does not depend on galaxy formation at all. Boylan-Kolchin says so directly in the paper. The requirement, in his words, does not rely on assumptions such as abundance matching, but is simply a statement about the distribution of collapse mass in the universe as a function of time, and about the reservoirs of ordinary matter associated with that collapse mass. He is not modelling stars, he is counting atoms. Now, the second half of the argument, and this is where it turns. How many big halos exist at a given moment in cosmic history? That is calculable, and the answer has an extremely unforgiving shape. Halos of modest mass are common. Halos of larger mass are less common, but the relationship is not gentle. The number falls off exponentially at the high end, which means that as you go up in mass, you're not losing objects steadily. You are falling off a cliff. Double the mass and you do not halve the count. You divide it by thousands, and that cliff moves with time. Early on it sits very low because gravity has not had long to work. As the universe ages, the cliff edge slides upward, and larger structures become statistically permissible. Between the universe being about 180 million years old and about 640 million years old, an interval shorter than the time since the dinosaurs died, the maximum available stellar mass at a fixed rarity increases by a factor of about 100. Try standing on that cliff for a moment. Imagine the early universe laid out in front of you as a landscape, where the height of the ground represents how much mass a structure holds, and the density of the ground represents how many of them there are. Down at the low end, you are walking through something like a crowd. Small halos everywhere, shoulder to shoulder, more than you could count in a lifetime. As you climb, the crowd thins, not gradually. You take a step and half of them are gone. You take another and half of what remains is gone. Higher still, and you're walking through open country, then through emptiness with occasional figures in it, then through emptiness. And then, quite abruptly, there is no more ground, not fewer objects, none. You're standing at the point where, in the entire volume of the observable universe at that moment, the total inventory drops to something you could count on your fingers, and one step beyond that the inventory is 0. Not because anything forbids it in principle, but because gravity has simply not had the time. That edge is not a wall someone built. It is the leading front of how much work gravity has managed to do since the beginning, and at 500 million years it has not done very much. So this is the arithmetic. Take the reported stellar masses of the most extreme early galaxies, divide by the baryon fraction to get the smallest halo that could possibly contain them. Then ask how many halos that size existed at that moment. For the 2 most extreme candidates reported in the first wave of results, the required efficiencies came out at 0.84 and 0.99, 99%. Every atom of ordinary matter the halo was ever allocated converted into stars, with essentially nothing left over. Boylan-Kolchin's word for that was physically implausible, and to understand why, compare it to the real universe around us. His line is worth quoting as written. In the low redshift universe, such efficiencies are never seen, with the efficiency below about 0.2 for all galaxies. 20% as a hard observed maximum anywhere. And even that is misleading, because 20% is the record. A large review of galaxy formation efficiency put the general case starkly. At its very best, galaxy formation converts something like 20 to 30% of available ordinary matter into stars, and that peak occurs only at one particular halo mass, right around the mass of the halo our own galaxy sits in, which the authors call the pivot mass. Above it and below it, galaxy formation gets less efficient, not more. Small galaxies lose their gas to exploding stars because their gravity is too weak to hold on to it. Large galaxies lose theirs to the black holes at their centers, which heat it and drive it out. The Milky Way is close to the most efficient thing in the sky at turning gas into stars, and it still only manages a few percent of its halo's total mass. Against that, 99% is not a stretch. It is a different category of claim. There is one more way to feel how extreme this is. Astronomers measure the rarity of a structure by something called peak height, which is a way of asking how far out on the tail of the distribution an object sits. The early galaxies in question require a peak height of at least 4.5, even assuming perfect efficiency. At that level, no more than about 6 parts in 100,000 of all the ordinary matter in the entire universe is inside anything large enough to host them, and Boylan-Kolchin supplies the comparison that makes it land. A peak height of 4.5 today corresponds to a halo of about 5 quadrillion solar masses. That is not a galaxy. That is one of the largest galaxy clusters in existence. Thousands of galaxies bound together, the sort of object that shows up in surveys as a named landmark. So the claim being made, when the data was taken at face value, was that objects as statistically extreme as the largest structures in the present-day universe were already sitting there 500 million years in, having converted essentially all of their available matter into stars with an efficiency never observed anywhere, ever. That is what impossible means when it is used carefully. Now let me hold the line on honesty, because this is exactly the point where a video like this could cheat, and I am not going to. The efficiency never actually went above 1. It went to 0.99. Boylan-Kolchin's own phrase in the abstract is that the observations sit at the very edge of these limits. At the edge, not past it. He also notes that the mathematical tool he used overestimates the number of massive halos at these times by 20 to 50% compared to full simulations, which means his constraint is deliberately generous to the data. And he was careful, in a way the coverage was not, to list 4 ways out rather than declaring victory. Star formation might really be that efficient early on. The recipe for converting light into mass might be wrong. The telescope's calibration might shift, or the small patch of sky being surveyed might simply be a fluke. 4 doors. 3 of them we will come back to at the very end of tonight. The second one is where we are going. Because that door, the one about the recipe, was the one nearly everyone walked through. It was elegant, it was physically motivated, and it was proposed by the same people who had raised the alarm. But before we open it, there is something you should know about this problem that changes how you will hear the rest of it. It did not start with the new telescope. It is much older than that, and the last time astronomers were certain they had found a galaxy that could not exist, they were wrong in a way that should have made everybody more careful than it did. Part 4. The problem is older than the telescope. Almost every account of this story begins in 2022 with a new telescope and a shock. That framing is convenient and it is wrong, and the wrongness matters, because the real chronology tells you something the short version hides. This problem was found, named, argued over and partially explained before the new telescope had even left the ground. Go back to 2004. A team led by Andrea Cimati, working with a survey on the Very Large Telescope in Chile, published a result on 4 galaxies at a distance corresponding to a universe roughly 4 billion years old. 4 galaxies does not sound like much, but these 4 were old. They were fully assembled, smoothly shaped, and each held more than 100 billion times the mass of the Sun in stars, with no ongoing star formation to speak of. In a universe that was supposed to still be busy stacking small things into larger ones, here were 4 finished products. The same year, a group led by Carl Glazebrook, using a survey on the Gemini telescope, found something similar and more damaging. Very massive, very red, evolved galaxies at a distance where the universe was about 3 billion years old, and not as curiosities, but making up something like 30% of all the stellar mass in existence at that time. A companion analysis found their typical ages ran between 1 and 3 billion years, in a universe that had only had a few billion to work with. This produced a term that has been quietly annoying theorists ever since: downsizing. The observation that the biggest galaxies appear to have formed first and fastest, and the smaller ones came along later, which is precisely upside down from a model whose central claim is that you start small and stack upward. It is sometimes called the anti-hierarchical problem, which is about as blunt as a name can get. Then, in 2005, comes the episode that everyone in this field should have taped to their wall: a team using both Hubble and the Spitzer infrared telescope announced an object catalogued as HUD FJD2. They placed it at a distance corresponding to a universe about 800 million years old, and they measured a stellar mass around 8 times that of the entire Milky Way, something like 600 billion suns assembled in the first 6% of cosmic history. NASA put out a press release. The nickname it acquired was the Big Baby Galaxy. Read the coverage from that year, and you will find, almost word for word, the arguments that would be made 17 years later. A galaxy that should not exist, a model that cannot accommodate it, a universe apparently building far faster than anyone allowed for, and it was not there. 2 years later, a mid-infrared analysis showed the object was almost certainly not at that distance at all. It was a dusty, luminous, infrared bright galaxy at less than half the distance, and the dust inside it had reddened its light in a way that mimicked the signature of an object at the dawn of time. The break in the spectrum that had been read as the fingerprint of extreme distance was something else entirely. Sit with that for a moment, because it is the emotional heart of everything that follows. Nobody lied. Nobody cut a corner. The team used the best instruments available, applied the standard analysis, got a result, checked it against the model, found a tension, and reported it. Every step was defensible, and the answer was wrong. Not slightly wrong, not off by a factor of 2, but wrong about what kind of object it was and where in the universe it sat. The mistake was, at the time, completely indistinguishable from a discovery. It looked exactly like finding something. It had the same shape, the same excitement, the same press release, and a group of careful people had to live inside that wrong answer for 2 years, giving talks about it, before the correction arrived. That is not a story about incompetence. It is a story about what it actually feels like to work at the edge of what an instrument can do. The edge does not announce itself. It looks like signal. There is a further lesson buried in how that correction happened, and it is one you will want in your pocket for the rest of tonight. There are exactly 3 things that can make a young, ordinary galaxy masquerade as an ancient, enormous one, and all 3 of them have caught professionals out. The first is dust. Dust scatters short wavelength light more effectively than long wavelength light, which is why sunsets are red and why a dusty galaxy is red. It is also why an old galaxy is red. Its blue stars are gone. From colours alone, those 2 conditions can look identical. The second is emission lines. A galaxy in the middle of a violent burst of star formation is surrounded by glowing gas, and that gas emits at a handful of extremely specific wavelengths, very brightly. Stretch those lines by cosmic expansion until they land inside one of your camera filters, and that filter suddenly reads bright, which the analysis interprets as a step in the underlying continuum, which is the signature of an evolved population. A young galaxy shouting can be mistaken for an old galaxy sitting still. The third is a black hole. Material spiraling into a supermassive black hole glows fiercely, and if it is wrapped in dust it glows red. That red light gets added to the galaxy's total, and a fitting program that has not been told to expect a black hole will assign that light to stars, old ones, because of the colour, and then charge the galaxy for the mass of stars that would be required to produce it. Dust, emission lines, and a hidden black hole. Hold those 3. Every single one of them is going to come back and take down a headline result. The problem did not go away after that, though. Through the 2010s, a sequence of surveys with names like ZForge and UltraVista and Candles kept finding massive evolved systems earlier than they should be. Not sensational single objects, populations, a steady accumulation of galaxies at distances where the universe was 2 or 3 billion years old, already finished, already read. In 2017, Glazebrook's group nailed one of them down properly with a spectrum rather than colours. An object catalogued as ZF Cosmos 2115, at a distance corresponding to a universe about 1 3/4 billion years old, holding 170 billion solar masses of stars, showing an absorption line spectrum with no ongoing star formation at all, and an inferred age of roughly half the age of the universe at that moment. Before the new telescope, that object was the record, the earliest dead galaxy anyone had confirmed, and then, in 2016, 4 astronomers, Charles Steinhardt, Peter Kapok, Dan Masters and Josh Spiegel, collected the whole thing into a paper and gave it the name it has carried ever since, the impossibly early galaxy problem published in the Astrophysical Journal. Their argument was the halo counting argument. 6 years before Boylan-Kolchin would sharpen it. If you take the relationship between starlight and halo mass that we measure in the nearby universe, and you apply it to the galaxies that surveys were finding at these early times, the surveys report, and this is their phrasing, several orders of magnitude more halos in the trillion to 10 trillion solar mass range than it is possible to have formed by those redshifts. Several orders of magnitude, not a discrepancy, a category error somewhere, and notice the escape hatch they built into the sentence. If you take the relationship between starlight and halo mass that we measure in the nearby universe, the conditional is doing enormous work and they knew it. Their own preferred resolution, stated in the paper, was that the recipe changes, specifically that the early universe made proportionally more massive stars, which would mean the light we see requires less mass behind it than we have been assuming. Which is to say, the solution that would dominate the next decade of this argument was already on the table in 2016, proposed by the very people raising the alarm before a single one of the famous images had been taken. So when the new telescope launched on Christmas morning of 2021 and started returning data 7 months later, it was not walking into an empty room. It was walking into a 20-year-old argument with a named problem, a proposed solution, and at least one cautionary tale about a galaxy that had turned out to be a smear of dust in the wrong place. What it did was make everything sharper. It could see further, which extended the problem into territory nobody had been able to test, and crucially, it could do something the earlier surveys mostly could not. It could take a proper spectrum of these things, spreading their light out by wavelength and reading the fine structure directly, instead of guessing from colours. That capability was going to matter enormously. It would confirm some of the impossible galaxies beyond argument, and it would quietly destroy others. Part 5. The machine built to look at the beginning. Before we get to what it found, it is worth understanding what the James Webb Space Telescope actually is, because the design was not a general-purpose upgrade. Nearly every unusual thing about it exists to solve one specific problem, and that problem is the one we're talking about tonight. The mirror is 6.5 meters across, made of 18 hexagonal gold-coated beryllium segments that had to be folded to fit inside a rocket and then unfolded once correctly, with no possibility of repair. Below it sits a sun shield the size of a tennis court, 5 separate layers of a plastic film thinner than a human hair, whose entire job is to keep one side of the spacecraft in permanent shadow. And the whole assembly sits about 1.5 million kilometers from Earth, 4 times further away than the Moon, at a gravitational balance point where it can keep the Sun, the Earth and the Moon all behind that shield at once. All of that exists so the telescope can be cold. Around 40 degrees above absolute zero cold. Because the thing it was built to see is infrared light, and anything warm glows in the infrared, including a telescope. A warm telescope looking for faint infrared light is like trying to photograph a candle from inside a bonfire. Why infrared? This is the part that makes the whole enterprise possible, and it comes straight out of the expansion of the universe. Light travelling through expanding space gets stretched. The wave that leaves a distant galaxy is not the wave that arrives. Space itself has grown while the light was in transit, and the wavelength has grown with it. We call this cosmological redshift, and it is the ruler we use for distance. The further away something is, the longer it has been travelling, the more space has expanded underneath it, and the more its light has been stretched toward the red end and beyond. For the galaxies at the frontier of this story, the stretching factor is enormous. Light that left as ultraviolet, the short energetic light produced by young hot stars, arrives at Earth stretched by a factor of 15 or more, which drops it into the mid-infrared. Hubble simply could not see it. Neither can any telescope on the ground, because the atmosphere absorbs and glows in exactly those wavelengths. There was no way to do this from Earth. There was no way to do it with the previous generation of space telescopes. There was one way to do it, and it cost about $10 billion and 20 years. Now how the actual discovery works, because this matters enormously for the corrections coming in the next part. There are 2 stages. The first is photometry, which is just taking pictures through different coloured filters and comparing how bright the object is in each one. From the pattern of brightnesses you can make a fairly good guess at how far away something is, because the stretching of the light shifts recognisable features from one filter into another. You can also guess at the stellar population, because a red ratio suggests old stars and a blue ratio suggests young ones. This is fast, it works on faint objects, and you can do it on thousands of galaxies at once. The second stage is spectroscopy, which means spreading the light out by wavelength and reading it properly. Instead of 4 or 5 numbers, you get a continuous curve with individual emission and absorption features in it, and those features sit at wavelengths determined by atomic physics, so you can measure the stretching factor directly rather than inferring it. This is slow, it requires far more light, and until this telescope it was essentially impossible at these distances. The relationship between the two is worth stating plainly, because it explains most of the drama in this field. Photometry proposes, spectroscopy disposes, and the instrument that does the disposing is worth a sentence of its own, because it is one of the strangest devices ever flown. To take spectra of many faint objects at once, you need to let each one's light through a separate slot, while blocking everything around it, otherwise the sky and the neighbours swamp the signal. So the telescope carries a grid of roughly 250,000 microscopic shutters, each one about the width of a human hair, each one individually commandable, opened and closed by magnetic field. Point the telescope at a field, decide which of 250,000 doors you want open exactly those, and collect. It is the difference between hearing a crowd and hearing 9 specific people in it. So, July 2022. The telescope has been operational for a matter of weeks. One of the first datasets released to the community comes from a survey pointed at a strip of sky in the constellation Bootes, a region astronomers have been staring at for decades because it is unusually free of foreground junk. The patch is 38 square arc minutes. To give you that in terms you can hold, the full moon covers about 1,800 square arc minutes of sky. So this is roughly 1/50th of the area of the moon, a keyhole. Somewhere in the days after that release, a research team runs a colour selection across the field, looking for objects that show 2 particular breaks in their light. The pattern you would expect from a galaxy at the dawn of time with an already evolved stellar population. 13 objects fall out of the filter. Picture what that actually looks like on a screen. Not a spiral, not a photograph of anything you would recognise as a galaxy. A handful of dots, each a few pixels across, faint enough that you have to trust the software that they are objects at all. And the wrong colour. Too red. Far too red for what they are supposed to be. In a part of the universe that should contain nothing but small blue chaos, 13 small red points sitting quietly in the noise. 6 of them carry the headline. In 2023, Ivo Labbé and 10 colleagues published the result in the journal Nature, under a title that was careful in a way the coverage would not be. A population of red candidate massive galaxies 600 million years after the Big Bang. 6 galaxies, each apparently holding more than 10 billion times the mass of the Sun in stars, at distances corresponding to a universe between 500 and 700 million years old. And one of them, they wrote, with a possible stellar mass of roughly 100 billion suns, which is to say, an object with the stellar mass of the modern Milky Way, fully assembled when the universe was younger than the time since the first dinosaurs. The paper's own hedge is right there in the abstract, and I want to read it to you because it is the sentence that got left out of every single retelling. If verified with spectroscopy, they wrote, the stellar mass density in massive galaxies would be much higher than anticipated. If verified with spectroscopy, that was in the paper, in print, in Nature. And what happened next was that the world took the number and dropped the conditional. It is worth understanding why a result like this lands so hard, because it is not only about the number, it is about the direction of the surprise. If the telescope had found the early universe emptier than expected, nobody outside the field would have noticed. An absence is easy to explain. The instrument was not sensitive enough. The objects were behind dust. The survey was too shallow. Absences are cheap, but an excess is expensive. You cannot explain away something being there. You either have to accept it, or you have to show that it is not what it looks like, and showing that requires more observing time than finding it did in the first place. That asymmetry is why the early universe problem has the shape it does. Every time the telescope points somewhere new, it can only ever make the problem worse or leave it unchanged. There is no observation that makes an excess go away by finding less. The only thing that can undo an excess is a re-examination of the things already found, which is exactly what happened, and which is why the most important work in this story is the least visible. The coverage was enormous, and it went in 2 directions at once. The measured version, astronomers find galaxies that challenge models of galaxy formation, was accurate and reasonably well handled in the science press. The other version was not. Within weeks, the claim circulating on social media was that the James Webb Space Telescope had disproved the Big Bang, that the universe was secretly twice as old as we had been told, that the standard model of cosmology had collapsed and the institutions were covering it up. Neither version knew what was already happening in the background, because the moment those 6 objects were published, other teams began pointing the telescope's spectrograph at them, and the answers started coming back. Part 6. The Correction. Nobody covered. Here is the part of the story that has never been made into a thumbnail, and I suspect it never will be, because the shape of it is wrong for that. There is no reveal. There is just a slow, careful, uncomfortable process of people checking a result that everyone wanted to be true and finding that a great deal of it was not. Start with the first of the 6 to fall. It carried a catalogue number ending 13,050, and the colour-based analysis had placed it at a distance corresponding to a universe about 600 million years old, with a stellar mass around 8 billion suns. A team led by Dale Kaczewski put the spectrograph on it. The object was not at that distance. It was much closer by an amount that translates to nearly 1 billion extra years of cosmic history. And when they looked at its light properly, the reason for the red colour became obvious. There was a broad hydrogen emission line in the spectrum smeared across a range of wavelengths corresponding to gas moving at nearly 2,000 kilometers per second. Gas does not move that fast in a galaxy. Gas moves that fast when it is orbiting a black hole. The paper's title was Hidden Little Monsters, which is about as good as astronomy titles get. What the analysis had read as 100 million years of stellar evolution was, in fact, a dust-shrouded black hole eating. 2 more of the 6 moved. One dropped from a universe of about 530 million years to one of about 680. Another dropped by a similar amount. Neither of those is a catastrophic error. The objects are still early, still interesting. But each step closer to us takes a bite out of the stellar mass, because a nearer object producing the same apparent brightness is intrinsically fainter, and a fainter object needs fewer stars. A 4th showed the same broad hydrogen signature as the first, this time indicating gas at around 3,500 kilometers per second. Then, in 2024, a team using a survey called Rubies published what is still the most careful treatment of these objects, and it is the one you should hold in your head, because it refuses to be simple in either direction. 3 of the candidates, at distances corresponding to a universe between 600 and 800 million years old, genuinely do show the break in their light that indicates an evolved stellar population. That part survived, which means starlight really does dominate their appearance at the relevant wavelengths, and their star formation histories really do stretch back hundreds of millions of years into a universe that had only existed for 600 or 700. But 2 of those 3 also show broad hydrogen lines, which means an obscured black hole is contributing to the light as well. And when the team ran a proper decomposition, trying to separate the stellar contribution from the black hole contribution, the answer for the stellar mass came out spanning a range from about 1 billion suns to about 100 billion suns. Read that again. A factor of 100 of uncertainty on the central quantity in the entire argument. The author's own verdict on every available explanation was a single word: incomplete. And then there is the study that gave the whole affair its epitaph. A group working with a Canadian-led survey examined 19 comparable candidates across 5 separate fields and found that their spectra told a different story again. The red colours were not coming from evolved stars. They were coming from extremely strong emission lines produced by ordinary, young, energetically star-forming galaxies. The second of our 3 impostors, caught in the act. Their masses, once properly fitted, were nothing remarkable. The paper is titled Lambda CDM Not Dead Yet. So look at what actually happened. In 2005, a team found an impossibly massive galaxy at the dawn of time, and it turned out to be dust in the wrong place. In 2023, a team found 6 impossibly massive galaxies at the dawn of time, and one of them turned out to be a black hole. 2 of them turned out to be closer than reported, and a whole comparable population turned out to be emission lines. The instrument had improved by a factor you could hardly overstate. The failure mode had not changed at all. That is the thing I want you to feel here, and it is not cynicism. It is closer to sympathy. Every one of those measurements was made by a competent person doing careful work at the absolute limit of what their equipment could do. At that limit, the signal and the artifact look the same. They have to. If they looked different, it would not be the limit. So the people working there are permanently in a position where the most exciting thing they could possibly find is also the thing they are most likely to be fooled by. And there is no way to know which you have got in the moment from the inside. You publish, and you wait, and other people check, and sometimes it holds, and sometimes it dissolves, and both outcomes look identical on the day you write the paper. Now, and this is essential, do not let me leave you with the impression that the whole thing evaporated. It absolutely did not. Some of these objects are rock solid, and the most solid one is the strangest. It is catalogued as Ruby's UDSQGZ7, and it sits at a distance corresponding to a universe 700 million years old, which is about 5% of its present age. Its spectrum was measured directly and published in 2025. It holds about 17 billion solar masses of stars. Every one of those stars formed before the universe was 640 million years old, and then it stopped. The analysis puts the shutdown somewhere between 50 and 100 million years before the light we are seeing left it. Here is the detail that makes it hard to look away from. It is 209 parsecs across. That is about 680 light years, and I want you to sit with the density that implies. 17 billion suns, in a volume that in our own neighbourhood would contain perhaps a few thousand stars. Its stellar density is comparable to the dense core of a modern giant elliptical galaxy, one of the finished ancient red objects at the centres of galaxy clusters, the endpoints of 13 billion years of merging. Except, this is not an endpoint. This is the beginning, and it is already finished. Its spectrum shows no emission lines at all. None. That absence is what makes calling it dead a scientific statement rather than a rhetorical one. There is no glowing gas, no ongoing star formation, nothing being lit up. Just a break in the continuum, absorption features, and silence. And the number attached to it is the one that should worry you. The implied abundance of massive dead galaxies in the first billion years is more than 100 times larger than any model predicts, a factor of about 150. When a simulation team went looking through their virtual universes for anything resembling it, they could not produce one. And it is not alone in surviving. The two current distance record holders have both been confirmed with spectra rather than colours, which means their distances are not in question at all. One of them, called JD's GSZ 14-0, sits at a point when the universe was about 290 million years old, and it is not a faint smudge. It is the second most luminous object with a confirmed spectrum anywhere beyond a certain distance. It is roughly 1,600 light-years across. It is forming stars at more than 20 solar masses a year, and in March of 2025, a radio observatory in Chile detected oxygen in it. Oxygen, an element that has to be manufactured inside a star and then released by that star's death, present in measurable quantity in a galaxy we are seeing at 2% of the universe's current age. The team's summary was direct. These properties add to the evidence that luminous massive galaxies were already in place less than 300 million years after the beginning, at number densities more than 10 times higher than anything extrapolated from before the telescope launched. The other record holder, confirmed in 2025 and published in January of this year, sits at 283 million years and carries the most uncomfortable statistic in the entire field. The number of bright galaxies at that epoch is not 10 times the prediction. It is around 180 times the prediction. So we are left in an awkward position. Several of the loudest results have been walked back or heavily qualified, and the problem is still there, sitting underneath them, refusing to move. Which brings us to the question this whole video is actually about. Not what the telescope found, but what the number attached to what it found actually is. Because I have said the word mass 40 times tonight, and I have not once told you where it comes from. Part 7. What we have actually been measuring. I told you at the start that we have never weighed a galaxy. I want to make good on that now, properly, because this is the section where the ground moves, and once it has moved, it does not move back. There is no scale. I mean that with complete literalness. There is no instrument anywhere that has ever been placed beneath a galaxy and given a reading. There is no method by which anyone has ever directly determined how much matter is in a distant object. What we have is light. That is the entire input. Everything else in the sentence, "This galaxy contains 100 billion solar masses of stars," is arithmetic performed on that light, and the arithmetic has steps, and one of those steps is not a measurement at all. Let me walk it with you, one link at a time. The first link is the easiest. You collect photons, you count them in each filter, or you spread them out and read the spectrum. This is genuinely measured, with known uncertainties, and everyone agrees on it. The second link is distance. From the spectrum you find features at known rest wavelengths, the sharp cutoff where neutral hydrogen absorbs everything shorter, the specific lines of oxygen and carbon, and you see how far they have been stretched. That gives you the redshift directly, and from the redshift plus the expansion history you get a distance. This is solid too, provided you have a spectrum. Where it goes wrong is when you only have colours, which is how 3 of the 6 original candidates ended up in the wrong place. The third link converts apparent brightness into actual output. If you know the distance, you know how much light the object is genuinely producing because brightness falls off in a completely understood way. Fine, still solid. Now the fourth link, and this is where it stops being a measurement. You have the total light, you want the total mass. To get from one to the other, you need to know how much mass is producing each unit of light, the mass-to-light ratio. And here you run into a fact about stars that is so lopsided it borders on the absurd. Stars do not shine in proportion to their mass. They shine in proportion to roughly their mass raised to the power of 3.5, which means a star 10 times heavier than the Sun does not put out 10 times the light. It puts out something like 3,000 times the light, and a star 1/10 the Sun's mass does not put out 1/10. It puts out about 3,000ths. Now take that and apply it to a whole galaxy full of stars. In an old stellar population, roughly 95% of the light you receive comes from stars in a narrow band between about half the Sun's mass and about 1 solar mass. That is where the visible action is. Meanwhile, roughly 70% of the actual stellar material, the mass, the substance, the stuff, sits in stars below half a solar mass, which contribute almost nothing to what you can see. So here is the situation you're in when you point a telescope at a galaxy 13 billion light-years away. The light is coming from one population, the mass is sitting in a different population, and the second population is, for all practical purposes, invisible. Let me put you inside that for a moment. Imagine you could stand somewhere inside one of these galaxies and count what is around you. The first thing you notice is a handful of enormous blue stars, and they dominate everything. They are so bright that they wash out your view of anything near them, and if you were judging the population by what you could see, you would conclude it was mostly made of these. Then, as your eyes adjust, you find the middle, an enormous number of ordinary stars, sun-like and a little smaller, doing most of the visible work of the galaxy. And then, if you could adjust further than any eye can, you would start to find the others. Beneath everything, in numbers that dwarf everything above them, the small red ones. Dim, cool, enormously long-lived, and so faint that the nearest one to Earth was not discovered until 1915, and cannot be seen from anywhere on this planet without a telescope. 7 kilograms out of every 10 of stellar material in that galaxy is sitting in those stars, and you cannot see a single one of them from where you are standing. The stars doing the shining are not the stars doing the weighing, which means that to convert light into mass you must assume something about a population you have never observed. You must assume how many faint stars accompany each bright one, and that assumption has a name. It is called the initial mass function, and it is the recipe. For every batch of stars a galaxy makes, how many of each size does it produce? It was written down in 1955. A physicist named Edwin Salpeter published a paper in the Astrophysical Journal, and in it he fitted a single power law to the distribution of stellar masses. The number of stars falls off as mass to the power of minus 2.35. That is the whole thing. 1 exponent minus 2.35. Where did he get it? From the stars in the solar neighbourhood, the ones near enough to count properly in the 1950s, and he fitted it over a range from roughly 4/10 of a solar mass up to about 10. That number, from that neighbourhood, over that range, is what modern astronomy carries out to the edge of the observable universe. To be clear about what Salpeter did and did not do, it was excellent work, and it was honest work, and he was not claiming a universal law of nature. He was describing the stars he could count. The extrapolation is ours, not his. We took a fitted curve from a small local sample and used it as a physical constant for objects that formed under conditions that share almost nothing with the solar neighbourhood. Different chemistry, different temperatures, different densities, different everything. There was never a good reason to expect it to hold. There was simply no alternative on offer. It has been refined, of course. In 2001, Pavel Krupa proposed a version that bends. The slope flattens below half a solar mass and flattens again in the brown dwarf regime. 2 years later, Gilles Chabrier proposed a smooth alternative that behaves almost identically in practice. Both are better fits to the local data than a single straight line, and the difference between them and Salpeter is not academic. A Krupa recipe gives you roughly half the mass of a Salpeter recipe for exactly the same amount of light, because it has fewer of those invisible little stars hiding underneath. Half. Just from choosing a different curve. Now the vocabulary, because we are going to need it constantly from here. A top-heavy recipe means proportionally more massive stars than the local one. Since massive stars are so absurdly bright, a top-heavy population is a very efficient light-producing machine. You get more shine per kilogram. So if the early universe was top-heavy, every observed galaxy needs less mass than we have been charging it for. A bottom-heavy recipe means proportionally more of the small faint ones. That is the opposite. A bottom-heavy population is dragging around an enormous quantity of dark, quiet material that produces almost no light, so the mass required to explain a given brightness goes up. And there is a bookkeeping number astronomers use to keep track. It compares the mass-to-light ratio you get when you let the recipe float freely against the ratio you get when you assume the Milky Ways. If it comes out at 1, the galaxy is like ours. If it comes out at 2, the galaxy is carrying twice the mass you would otherwise have assigned it, and the extra is all in stars you cannot see. There is a fifth link, incidentally, and it is worth naming because it is where the impossibility actually gets declared. Once you have a stellar mass, you have to work out how big a dark matter bowl was required to hold it, because that is the quantity Boylan-Kolchin's ceiling applies to. And that step requires assuming an efficiency. What fraction of the halo's ordinary matter turned into stars? So the chain does not end at the assumption. It ends at an assumption resting on an assumption. I want to be scrupulous here, because none of this is hidden. Astronomers do not pretend the recipe is measured. Every paper in this field states which recipe it used, precisely because everyone understands that the choice matters. Labbé's paper says it used Salpeter's. Boylan-Kolchin's paper explicitly lists the recipe as one of his 4 ways out. Steinhardt's original paper proposed changing it. The profession has been entirely upfront about this for 70 years. What happens is that the caveat does not survive translation. A paper says, assuming a standard recipe, this galaxy contains 100 billion solar masses. A press release says, this galaxy contains 100 billion solar masses, and a comment section says, they found something impossible and they are hiding it. So, pull the 4th link and the entire chain moves. Every stellar mass in every catalogue in astronomy, every claim about how much a galaxy weighs, every calculation of whether it could have formed in time, which raises the obvious question, and it is the question that occupied a decade of very good people. What if the recipe changed? Part 8. The escape hatch. The proposal was that the early universe made bigger stars, and I want to be very clear about the status of this idea before we take it apart, because it would be easy to present it as a convenient excuse invented to save a model, and it is nothing of the kind. It is one of the better motivated ideas in astrophysics. It follows from thermodynamics, and if you had asked a theorist in 1990, before any of this was a controversy, whether the first stars should have been more massive than the ones forming today, they would have said yes without hesitating. Here is why. A cloud of gas floating in space is having an argument with itself. Gravity is trying to pull it inward. Pressure, which comes from heat, is pushing it outward. As long as pressure wins, nothing happens. When gravity wins, the cloud collapses and stars form. The threshold where gravity wins depends on temperature and density, and it is called the Jeans mass. The relationship is not complicated. The colder the gas, the smaller the piece that can collapse. Warm gas can only collapse in big chunks, because a small chunk of warm gas is still too pressurized to fall in on itself. Cold gas can collapse in small chunks, so the characteristic size of the stars a cloud produces comes down, almost entirely, to how cold that cloud managed to get before it fell apart. Which brings us to the question of how gas cools, and this is where the early universe is genuinely structurally different from anywhere we can observe directly. To cool, a gas has to convert its heat into light, and let that light escape. Individual atoms are not good at this at low temperatures. They need a lot of energy to be excited at all. Molecules are better because they can rotate and vibrate, and rotating and vibrating takes small amounts of energy, which means molecules can radiate away heat when atoms cannot. In a universe with no elements heavier than helium, the only molecule available in any quantity is molecular hydrogen, and molecular hydrogen is frankly mediocre at this job. It is a symmetric molecule, which limits how it can radiate, and below about 200 Kelvin it essentially stops helping. So a primordial cloud collapses, warms up, radiates as best it can with the one tool it has, and hits a floor at around 200 Kelvin. It cannot get colder, and a cloud that cannot get colder than 200 Kelvin has a Jeans mass of a few hundred times the mass of the Sun. That is the argument. In its cleanest form, it says, the first stars had to be enormous, because the universe had not yet manufactured the ingredients required to make small ones. Everything changes once stars start dying. A dying star throws carbon and oxygen and iron back into space, and those elements are excellent coolants. Carbon and oxygen in particular radiate efficiently at low temperatures through what are called fine structure transitions. Better still, at high densities, the heavy elements condense into solid grains of dust, and dust is a superb radiator. Put dust into a collapsing cloud and it can reach about 10 Kelvin. 10 Kelvin instead of 200. And since the Jeans mass scales with temperature to the power of 1.5, that is a difference of a factor of roughly 100 in the characteristic mass of the fragments. So small stars are not a default feature of the universe. Small stars are a consequence of previous generations of stars having died and left their ashes behind. Every red dwarf that will still be burning 1 trillion years from now exists because something enormous burned out first and made it possible. Simulations bear this out with some precision. Work on turbulent cloud collapse across a wide range of chemical enrichment finds that dust cooling starts permitting genuinely small stars once the heavy element content reaches about 100,000th of the Sun's, but that the overall distribution stays weighted toward the heavy end until the enrichment reaches around 1% of solar, which is a level the earliest galaxies had not yet reached. And then there is the version of this argument that I find the most quietly elegant thing in the whole story. The cosmic microwave background is not just an image of the early universe, it is a bath. It fills all of space, and it has a temperature, and that temperature was higher in the past, because the light has been stretched by expansion ever since, and stretching light lowers its energy. Run the clock backward and the background gets warmer. Now, the gas in star-forming clouds in our galaxy sits at around 20 Kelvin. That is the working temperature at which the Milky Way builds stars. In 2018, 3 researchers, Adam Germin, Charles Steinhardt and Josh Spiegel, pointed out that the temperature of the cosmic background exceeds 20 Kelvin above a redshift of 6.3, which corresponds to a universe roughly 900 million years old. Think about what that means. Before that moment, no cloud anywhere in the universe could be as cold as the clouds that make stars in our galaxy today. Not because of local conditions, not because of chemistry, but because the sky itself was warmer than that. There was a floor under the entire cosmos, and it was above the temperature at which the Milky Way does its work. Their conclusion in the paper is stated plainly. The recipes in most star-forming galaxies above that redshift are expected to be different from the ones derived from observations of our own galaxy. Not might be, are expected to be. On thermodynamic grounds alone before you look at a single galaxy. So the escape hatch is not a patch. It is close to a prediction, and there is corroborating evidence from an unexpected direction. The estimated masses of the first generation of stars have been falling for 20 years, as simulations gained the resolution to see what actually happens inside a collapsing primordial cloud. The early work said 1 star per cloud, hundreds to 1,000 solar masses. Then higher resolution work found that the disks around those forming stars are unstable and break into pieces, and the answer dropped to a few tens to a few hundreds. More recent work finds that when a whole cluster of fragments forms, they compete for material and starve each other, dropping the maximum further. And a study from last year found that magnetic fields, of all things, limit the mass of the first stars more effectively than radiation does. The direction of travel is consistent, and it is downward, which is an interesting thing to notice about an idea whose usefulness depends on the early universe making things upward. Now, the number that matters. How much does a top-heavy recipe actually buy you? Steinhardt's original paper estimated that plausible changes to the recipe move inferred stellar masses by a factor of 3 to 10. In 2023, his group went further and rebuilt the fitting templates from scratch, arguing that the standard ones contain 2 impossibilities: stellar populations older than the universe at the relevant times, and a recipe that the temperature argument forbids. With corrected templates, the inferred masses dropped by a factor of 10 to 40. Their verdict at the time was a single sentence: and you can hear the relief in it. The stellar masses are no longer seemingly inconsistent with the standard model. A large simulation project reached a compatible conclusion from the other end. At a fixed observed brightness, a top-heavy population sits about a factor of 16 lower in stellar mass than a normal one, because the enormous stars are doing so much of the shining. And then, in July of this year, a piece of direct evidence arrived that made the whole idea feel considerably more solid. A team used the telescope to resolve individual stars in the Small Magellanic Cloud, a small, chemically poor companion galaxy to our own, and counted more than 15,000 of them down to 16/100ths of a solar mass. That is the first time anyone has ever taken a proper stellar census of another galaxy that far down the mass scale. The slope they measured was -1.99. Salpeter's is -2.35, shallower, fewer small stars per big one, in a galaxy with less heavy element enrichment than ours, exactly as the cooling argument predicts. There was one more line of evidence, and I include it partly because of how it turned out. In 2024, a team studying a galaxy at a distance corresponding to a universe about 1 billion years old found a spectrum they could not explain with ordinary stars. The light was not being produced primarily by stellar surfaces at all. It was being produced by the surrounding gas, glowing after being blasted by radiation from something extraordinarily hot. To reproduce it, they needed stars with surface temperatures around 100,000 degrees, which meant roughly 10 times as many stars above 50 solar masses as a standard recipe allows. A follow-up study found 5 more candidates showing the same signature. That looked like direct confirmation. Then another group published a paper on the same object with the title, "No Top-Heavy Stellar Initial Mass Function Needed." Their argument was that a mixture of an accreting black hole and ordinary stars reproduces the spectrum without any change to the recipe at all. Our third imposter, back again, doing exactly the same job as before. So by any reasonable standard, the escape hatch was in good shape. The problem had a name, the solution had a mechanism, the mechanism had thermodynamic backing and a direct observational hint from a nearby galaxy, and the numbers came out roughly the right size. There was only one thing missing. Nobody had ever actually measured the recipe outside our own local corner of the universe. Part 9, The Other Crisis, and What Happened to It. Before we get to the measurement that changed everything, I want to take you sideways, because there has been a second crisis running in parallel this entire time, on the same data, from the same telescope, with the same structure. And what happened to it in the last 18 months is the single most useful thing you can know before you hear what happened in January. The second crisis is about black holes. Every large galaxy has one at its centre, and they are not modest objects. Ours is around 4 million times the mass of the Sun. The one in Andromeda is far larger, and the relationship between a black hole and the galaxy around it turns out to be surprisingly tight. Locally, a black hole comes in at roughly 0.1% of the galaxy's total stellar mass, and up to about 0.5% of the mass of the central bulge. That is not a loose correlation. It holds across a range of galaxy sizes spanning several factors of 1,000, which strongly suggests the black hole and the galaxy grew up together, regulating each other. So when the telescope started finding accreting black holes in the early universe, everyone knew what to check. The answer came back badly. A study of active galaxies at distances corresponding to a universe between 1 and 1.5 billion years old found that the black holes were, in their words, overmassive by 10 to 100 times, compared to their nearby counterparts in galaxies of the same stellar mass. Another survey found 12 more, some with ratios exceeding 10%, 100 times the local value, and one object in particular is very hard to argue with. It sits at a distance corresponding to a universe about 800 million years old, and its black hole holds about 400 million solar masses in a galaxy where that works out to something like 40% of the entire stellar mass. 40%. 1,000 times the local ratio. The obvious objection, that we only notice the extremes because bright things are easy to find, does not apply, because this one is not bright. It is dormant. It is barely eating at all. We found it anyway. Alongside that came the arithmetic problem, which is even harder to shrug off. Black holes grow by eating, and there is a hard speed limit on eating. As material falls in, it heats and radiates, and that radiation pushes outward on whatever is trying to fall in behind it. At a certain rate, the push balances the pull, and the black hole cannot accept material any faster. That limit means growth is exponential, with a characteristic doubling time, the time to grow by a factor of about 2.7, of roughly 45 to 50 million years. Now run the numbers. To grow 100 solar mass seed, left over from an early massive star, into a billion solar mass monster, you need about 16 of those doublings. 16 times 45 million is around 725 million years. And the universe, at the point where we observe the most distant quasars, has been running for about 670 million years. It does not fit. It does not fit even if the black hole eats continuously at the maximum possible rate from the moment it forms, never pausing, never being interrupted for the entire history of the universe up to that point. And in July of this year, a European survey pushed the record further out still. 31 new quasars found in one go, the most distant now sitting in a universe about 670 million years old, which took the total count of confirmed quasars at those distances from 9 to 23. So there was a second impossibility, apparently independent of the first, apparently confirming it. And then there were the little red dots. They started appearing in the data almost immediately. Extraordinarily compact objects, typically only 150 parsecs across, red in the optical and blue in the ultraviolet, appearing in enormous numbers at distances corresponding to a universe roughly 1 to 1.5 billion years old, and then vanishing. About 1% of galaxies at those epochs have one. They had all the signatures of accreting black holes, broad emission lines indicating fast-moving gas, and if you took those signatures at face value, the implied black hole masses were absurd for the time available. But they had a problem. Several problems, actually. They were essentially invisible in X-rays, which accreting black holes are not supposed to be. They were quiet in the radio. They did not vary in brightness the way a feeding black hole should. And when a team looked carefully, they found a confirmed deficit of both hot and cold dust in the brightest of them, which is exactly backwards, because the standard picture of an obscured black hole requires a thick donut of dust to do the obscuring. Everything about them said, this is a black hole, and several specific things about them said, this is not a black hole. In January of this year, that knot came apart. A team led out of Copenhagen published a paper in Nature proposing that the broad emission lines are not broad because the gas is moving fast. They are broad because the light is being scattered by free electrons in a dense ionized cocoon wrapped around the object, and electron scattering smears a spectral line in a way that mimics motion. Underneath the smear, the intrinsic line is narrow. If you measure the intrinsic line instead of the smeared one, you get a different mass, much different. Their result, black hole masses between 100,000 and 10 million solar masses, 2 orders of magnitude lower than the previous estimates, a factor of 100, gone in a single paper. And the cocoon explains the missing X-rays and the missing radio and the absence of variability because you're not seeing the black hole at all. You're seeing the reprocessed glow of the material around it. In June, a further result strengthened the case considerably. A 30-hour spectrum of one such object, magnified by gravitational lensing to the equivalent of 80 hours, in which more than 40 separate spectral lines all converged on the same interpretation. And then there is the one that hurts. In 2023, a team announced what appeared to be the single most important object in high-distance astronomy. Catalogued as UHZ1, it sat at a distance corresponding to a universe 470 million years old. They detected it in X-rays with a space telescope, inferred a black hole of around 40 million solar masses, and noted that the host galaxy contained only about 170 million solar masses of stars. A black hole nearly as massive as the entire galaxy around it, 470 million years in. It was presented reasonably as the best evidence anyone had ever found for a black hole that formed directly from collapsing gas rather than from a dying star. In March of this year, a different team went back to it. They assembled 2.2 million seconds of X-ray exposure, including nearly 1 million seconds of new observation, and reanalyzed the detection 6 separate ways, varying the reduction and the astrometry. The signal, which had originally been reported at above 4 standard deviations, came out between 2.3 and 2.9. The softer X-ray band showed nothing at all, and when they ran 100,000 simulated tests shifting the assumed position by realistic amounts, they found that positional uncertainty alone can create or erase apparent signals of 3 to 4 standard deviations at that spot on the sky. Only 4 realizations in 10,000 reproduced the original claim. Then they pointed the mid-infrared camera at it in 9 separate filters covering everything from 5 to 25 microns. Nothing. Not in any of the 9. Not in the combined stack of all of them. Their conclusion, stated in the paper without decoration, no compelling evidence for such an object exists. None of the criteria you would expect are satisfied beyond reasonable doubt. UHZ1 was reclassified as what it now appears to be, a small, chemically poor galaxy forming stars at roughly 1 solar mass a year. An ordinary thing in an extraordinary place. And they left behind a sentence that I think is the most important sentence in this entire video. I am going to read it exactly. The long inference chain from raw counts to a black hole, mass of 10 to the 7 or 10 to the 8 solar masses, can propagate and amplify systematic errors to produce apparently compelling results that do not survive independent scrutiny. Sit with what that costs. For 2.5 years, UHZ1 was the crown jewel. It was in review talks and press releases and lecture courses. People built follow-up proposals around it. And it was, as far as anyone can now tell, a fluctuation in a very faint X-ray image at a position that was uncertain by about half an arcsecond. Nobody did anything wrong. That is the part that stays with me. They did careful work on data at the limit, and the limit did what the limit does. So notice the shape of the last 18 months. In the black hole crisis, every time somebody pulled hard on the inference chain, the numbers got smaller. Masses fell by 100. A landmark detection dissolved. The crisis did not vanish. The well-characterized individual objects are still there, still overmassive, still unexplained. But as a statement about the whole population, it is under serious pressure. That is what you would expect. That is what usually happens. Anomalies erode, which is exactly why what happened in January is so difficult to absorb. Part 10. The Reversal. January of this year was a strange month for this field. In the same few weeks that a paper in Nature cut the black hole masses by a factor of 100, a second group posted a result that went the other way. And almost nobody noticed because it was not about black holes, and it did not have a picture attached. The problem it set out to solve was the one nobody had solved for 70 years. The escape hatch depended on the recipe being different in the early universe. Nobody had ever measured the recipe anywhere except our own local neighbourhood. Not because astronomers had not thought of it, but because the measurement was, for all practical purposes, impossible. Here is why it is so hard. To count stars you cannot see, you need the ones you can see to tell you about them, and they do, faintly, through a peculiarity of stellar atmospheres. A small, dense, cool star has a much higher surface gravity than a large, puffy, luminous one. High surface gravity changes the pressure in the atmosphere, and pressure changes how spectral lines form. Some absorption features get deeper in dwarfs and shallower in giants, and a handful of them do the reverse. So there are fingerprints. A sodium doublet at around 8,180 angstroms, which strengthens when there are more small stars. A band of iron hydride at around 9,900 angstroms, discovered decades ago and named for the 2 astronomers who identified it, which is the cleanest indicator of all because almost nothing else affects it. A calcium triplet that runs the other way, weakening in dwarfs, so it works as a cross-check. The problem is that these features are subtle. They are shallow dips in a continuum, and to measure them reliably you need an enormous amount of light, signal-to-noise ratios that are routine for a nearby galaxy, and, until very recently, unreachable for a distant one. On top of that, the sodium feature is degenerate with how much sodium the galaxy actually contains, so you have to measure a second sodium line at a different wavelength just to separate the 2 effects. That is why it had never been done. Not once, beyond our own corner of the cosmos. The program that did it is called Inferno, which stands, with the acronym building enthusiasm characteristic of astronomers, for Initial Mass Function of Early Red Near-Spec Objects. It was led by Mariska Creek, Eliza Beveridge and Charity Cheng, and it ran on the 3rd and 4th of May, 2025, with a second visit later that month. Picture it. The telescope is 1.5 million kilometers out, in permanent shadow, cold. It turns to a patch of sky in the constellation Sextans, in a well-studied field where 9 massive, ancient, quiet galaxies happen to lie along the same enormous wall of large-scale structure. A filament of the cosmic web, seen edge-on 7 billion light-years away. The 250,000 shutter grid we talked about earlier does its work. A few dozen doors open, the rest stay shut, each open door framing one galaxy and nothing else, and then it holds. 31.2 hours of exposure on those 9 objects. What is it looking for during all that time? Not a galaxy, not a picture, a dip. A shallow depression in the continuum around 8,180 angstroms, produced by sodium atoms in the atmospheres of stars so small and so cool that they contribute almost nothing to the light being collected. 31 hours to measure the shadow cast by the population that does not shine. The stars doing the shining are not the stars doing the weighing, and for the first time somebody was going to weigh them anyway. To pull the answer out, the team combined that data with high-quality optical spectra from a survey on the Very Large Telescope in Chile, which had spent 128 nights collecting 20-hour exposures of galaxies in that distance range. Together, the 2 datasets covered the whole relevant span of the spectrum. Then they ran a fitting code that solved simultaneously for the age of the stellar population, the abundances of 18 separate chemical elements, and 2 independent slopes describing the low-mass end of the recipe. 46 free parameters, explored with 1,024 independent samplers running for 21,000 steps each. The paper appeared as a preprint in January and is currently under review at Nature Astronomy. Its title tells you the result before you open it. Bottom-heavy initial mass functions reveal hidden mass in early galaxies. All 9 galaxies came out bottom-heavy, every single one. More small stars relative to bright ones than our own galaxy makes. 4 of the 9 are inconsistent with a Milky Way recipe at better than 2 standard deviations, and the degree of bottom heaviness rises systematically with the galaxy's velocity dispersion, with its ion content, and with its total mass, the same pattern astronomers had already found in nearby galaxies, now demonstrated 7 billion years ago. That alone would be a landmark. It is the first robust measurement of the recipe beyond the local universe. Full stop. But it is the last part of the paper that matters for tonight. 2 of the 9 galaxies stand out. They carry catalogue numbers 1134,272 and 1166,579. They are the oldest objects in the sample. The fitted stellar ages come out at 6.1 billion and 7.5 billion years, in a universe that was only about 7 billion years old when that light set out, which means their stars formed almost immediately. And in the case of the older one, the fitted age runs right up against the age of the universe at that moment, with the uncertainty absorbing the difference. The formation redshifts work out above 6. Here is how the paper puts it. Assuming a typical star formation timescale of 1 to 200 million years, these 2 oldest galaxies were quiescent by a redshift of about 5.5 and are likely the descendants of the impossibly early galaxies discovered with the telescope. Descendants. Not analogues, not comparisons. The same objects seen 6 billion years later, after they had finished and gone quiet and been carried along by the expansion into a part of the universe where we can gather enough light to read them properly, and their recipes are the most bottom-heavy in the sample. Under the standard assumption, the first of them holds about 390 billion solar masses of stars. With the recipe measured rather than assumed, it holds about 1.5 trillion. The second goes from roughly 290 billion to about 870 billion, a factor of about 4 and a factor of about 3. Now feed that back into part 3. Boylan-Kolchin ceiling is a statement about how much stellar mass a halo can possibly contain. The reported masses were already requiring efficiencies of 84 and 99%, at the very edge of what conservation of matter permits. Multiply the stellar masses by 3 or 4, and the required efficiency does not go to the edge. It goes through it. The paper's own sentence is careful and devastating in equal measure. The formation redshifts of these 2 oldest and most bottom-heavy galaxies imply that the distant massive galaxies found by the telescope also had bottom-heavy recipes at early times, possibly making them a factor of 3 to 4 more massive than originally reported. These larger masses would suggest an even greater tension with galaxy formation models. And then a second sentence, which is worse. Their results additionally imply that the masses of the star-forming progenitors may also be underestimated, further heightening the tension. So the escape hatch is not merely closed. It was never a hatch. It was a door into a smaller room. Now, honesty, because this channel does not get to skip it just because the result is dramatic. 3 caveats, and the authors raise all 3 themselves. The first is that this is a preprint under review, not a published paper. It may change. That is how the process works, and I have spent an entire part of this video showing you what happens to results that do not survive review. The second is a real physical loophole, and they flag it explicitly. Their measurement constrains only the bottom of the recipe, the small stars. Above one solar mass, they hold the slope fixed at Salpeter's value, because their method cannot see up there. And they write plainly that if that upper slope is shallower than the Milky Way's, the stellar masses at high redshift can be reduced again. The third is a consistency check they ran on themselves. If you inflate every galaxy's stellar mass by a factor of 3 or 4, do the galaxies end up weighing more than their own gravity says they should? For 8 of the 9, no. The corrected stellar masses land right up against the dynamical masses, which is a remarkable kind of agreement. But the authors note the discomfort in it themselves. Agreement that tight leaves very little room for dark matter and gas inside those galaxies, which is its own small puzzle. And one object in the sample came out unphysical, with a stellar mass exceeding what its motions can support. They flag it, they explain why it is probably a disk seen face-on, and they do not hide it. So, not a proof, a first measurement, with its edges showing. But it is a first measurement that moved the number in the direction nobody wanted, and did it in the one place where the answer could not be dismissed as a modelling choice. Which leaves one obvious question, and it turns out someone had already answered it 2 years early without knowing what was coming. Part 11. Both at once. There is something I have been holding back for 2 parts, and it is time to hand it over, because it changes the shape of the January result considerably. The idea that massive galaxies are bottom-heavy is not new, it is 16 years old, and when it was first proposed it was every bit as unwelcome as it is now. In 2010, Peter Van Dockum and Charlie Conroy published a paper in Nature with a title that sounds mild and was not: A Substantial Population of Low-Mass Stars in Luminous Elliptical Galaxies. They had taken very high-quality spectra of 8 massive ellipticals in the Coma and Virgo clusters using a telescope in Hawaii, and they had detected, unambiguously for the first time, the sodium doublet and the iron hydride band we were talking about a moment ago. The same 2 fingerprints, the same method. 16 years earlier, and much closer to home. What they found was that those galaxies contain far more small stars proportionally than our own. Their conclusion was that low-mass stars make up more than 80% of the total number of stars in those galaxies, and more than 60% of the total stellar mass. 2 years later, a survey called Atlas 3D approached it from a completely different direction. Instead of reading absorption lines, they modelled the motions of stars in 260 nearby early-type galaxies, and asked how much mass was required to produce those motions. The answer came out the same way. The recipe is not universal. It shifts systematically from something Milky Way-like in small galaxies to something Salpeter-like or heavier in the largest ones. And crucially, that conclusion held regardless of what they assumed about dark matter, because inside the central regions of those galaxies dark matter contributes very little. Then a survey of nearly 25,000 galaxies from a ground-based sky survey confirmed the trend at scale, standard in small galaxies, steeper than Salpeter above a velocity dispersion of around 220 km per second. 3 completely independent methods: spectral fingerprints, stellar motions, and a statistical survey, all pointing the same way. And then there are the relics, which are the closest thing this field has to a time capsule. A relic galaxy is one that formed nearly all its stars in a short violent burst very early, and then simply stopped growing. Most massive galaxies keep accreting. They swallow smaller neighbours over billions of years and puff out into the enormous diffuse ellipticals we see today. A relic is one that never did. It got missed. It has been sitting there, compact and finished and unchanged, since the era we have been talking about all night. 3 of them are well studied, one catalogued as NGC 1277, another called Markarian 1216, and a third with a catalogue designation you would not enjoy me reading aloud. Their fitted recipes come out at low-mass slopes of 2.5, 3.0, and 2.8. Salpeter, remember, is 2.35. These are steeper than Salpeter, considerably more small stars than even the traditional heavy assumption allows, and their mass-weighted ages come out around 13 billion years, which puts their formation right back at the epoch this entire video is about. There is a detail in the study of the first of those that I keep coming back to. The bottom heaviness persists all the way out to the galaxy's outskirts, even though the velocity dispersion falls off steeply as you move outward. which means the recipe is not being set by local conditions at each radius. It was set once, globally, at formation, and then frozen. The galaxy carries a decision made 13 billion years ago in every part of itself. So the January measurement is not an isolated shock. It is the missing link in a chain that already existed. Nearby massive galaxies are bottom-heavy. Relics that formed earlier bottom-heavy, and now the same is measured in galaxies caught 7 billion years ago, whose formation puts them in the right era to be the survivors of the population in question. I should say that this is not unanimous, because it would be dishonest to present 16 years of literature as a clean consensus. There is a substantial critique arguing that the two main methods, the spectral fingerprints and the stellar motions, do not actually agree galaxy by galaxy, only on average, which is not the same thing and is a fair complaint. There is real tension between different groups measuring the same objects, with one influential analysis landing at a mass correction of about 1.6 and another, on the same mass range, landing at about 2.2. There is even a recent result finding the opposite effect, a deficit of small stars, in massive star clusters. This is a live field with genuine internal disagreement, and anyone telling you it is settled in either direction is overselling. Which leaves us with two solid results pointing in opposite directions, and this is where the story gets genuinely interesting rather than merely alarming. The physics says the early universe should have made bigger stars. That argument is good. The chemistry is right, the thermodynamics is right, the cosmic background really was warm enough to set a floor, and a nearby chemically poor galaxy really does show a shallower slope. The measurement says early forming massive galaxies are loaded with small stars. That result is also good, and it is now supported from three directions. How can both be true? In 2024, before any of this came to a head, Van Dockum and Conroy published a short paper proposing exactly that. Both. At once. They call it a ski slope recipe. Steep at the low mass end, more small stars than the Milky Way makes, and shallow at the high mass end, more enormous stars than the Milky Way makes. A distribution that is bottom-heavy and top-heavy simultaneously, with a deficit in the middle, around the mass of the Sun. The numbers they land on as a best fit are a slope of 2.40 below half a solar mass, 2.00 between half and 1, and 1.85 above 1. Compare that to Krupa's 1.3, 2.3 and 2.3, steeper at the bottom, shallower at the top, and here is why it works, in their own words. At the highest redshifts, the mass-increasing effect of a steep low-mass slope is more than compensated by the luminosity-increasing effect of a flat high-mass slope. Think about what that buys you. When a galaxy is young and still full of enormous short-lived stars, the top of the distribution dominates the light, and because there are more monsters than usual, the galaxy looks bright for its mass. So you infer less mass than you otherwise would. Then those monsters die within a few tens of millions of years, and what is left is the bottom of the distribution, which is heavy. So the same galaxy, observed billions of years later as a quiet red elliptical, weighs more per unit light than you would have assumed. One recipe. Two completely different apparent mass-to-light ratios, depending on when you catch it. The young version looks about 20% lighter than a Milky Way assumption would suggest. The old version looks about twice as heavy. They tested it directly on 3 of the early galaxies with confirmed evolved population signatures, and the masses came out a factor of 1.6 to 2 lower than the standard treatment. It is not obvious why nature would do this. They say so. Their proposed physical mechanism is that the two ends of the distribution might be controlled by two separate things, the low end by the gene's mass, which is about temperature, and the high end by the structure of turbulence in the collapsing cloud, which is about motion. Two knobs, no reason they should turn together, and there is now a hint that this is real. In June of this year, a survey of 214 actively star-forming galaxies did something nobody had done before. It measured both ends of the recipe in the same objects at the same time. The finding was that the two ends are only weakly correlated, and that they respond to different things. The low-mass end tracks the galaxy's chemistry. The high-mass end tracks its total mass and how much star formation it has done recently. Decoupled, as predicted, on different timescales. So there is a way out. There is a shape of recipe that reconciles everything, that has a plausible physical story behind it, and that now has a piece of direct observational support. And Van Dockum and Conroy, who proposed it, end their paper with a warning I think about constantly. I will read it as written. We acknowledge the long history of appealing to variation in the initial mass function as a means of explaining real or imagined observational tensions, and that in such previous cases a more prosaic explanation was usually found. We therefore suggest adopting the concordance recipe with caution, for now. The people who built the solution are telling you not to trust it yet, which is, I think, the single most reassuring sentence in this entire story, and it stands in almost perfect contrast to what has been said about all of this by people who are certain. Part 12. The people who say it is over. We have been careful all night, and I want to keep being careful now, because we are about to deal with the claims that started this whole thing circulating, and the fair way to handle them is to give each one its strongest form, in the words of the people making it, before saying anything about whether it holds. The first one has a single point of origin, which is unusual. In August of 2022, a man named Eric Lerner published an article under the title, "The Big Bang Didn't Happen." His argument was that the galaxies the telescope was finding at enormous distances have roughly the same apparent sizes as galaxies nearby, and that this is what you would expect if the universe is not expanding at all, and redshift is simply proportional to distance. Lerner is not an astronomer. He runs a fusion research company, and in 1991 he wrote a book called The Big Bang Never Happened, which advocates a framework called plasma cosmology, developed by the Swedish physicist Hannes Alfvén. So this was not a new position formed in response to new data. It was a 30-year-old position that had found a new headline. There is one detail in that article worth telling in full, because it is the clearest example of a particular technique that I have ever seen. Lerner quoted an astronomer named Alison Kirkpatrick, who had said, "Right now, I find myself lying awake at 3 a.m, wondering if everything I've done is wrong." That is a real quote. She said it, and in the context in which she said it, she was expressing something closer to exhilaration than despair. The feeling of a scientist watching a new instrument overturn assumptions faster than anyone can keep up with, which is the best thing that can happen to a person in that job. She has since explained this repeatedly. The words were accurate and the meaning was inverted. I should also tell you something that cuts the other way, in the interest of fairness. There is no peer-reviewed rebuttal to Lerner. The responses all live in science journalism, thoughtful, well-sourced pieces, but not papers. The professional literature has simply not engaged, on the grounds that there is nothing there to engage with. Whether you find that satisfying or convenient probably depends on where you were standing when you arrived. The second claim is more substantial, because it was made by a working physicist and published in a real journal. In 2023, Rajendra Gupta at the University of Ottawa published a paper in the monthly notices of the Royal Astronomical Society, proposing a hybrid model combining two ideas, coupling constants that change over time and tired light. Tired light is the old proposal that redshift is caused by photons losing energy gradually as they cross space, rather than by expansion. His result, which is the one you have seen quoted, it stretches the age of the universe to 26.7 billion years, with 5.8 billion years already elapsed by a redshift of 10 and 3.5 billion by a redshift of 20. If that were right, the early galaxy problem would evaporate because there would have been ample time. Now, here is the thing that almost nobody who quotes that number has noticed. It is in his own paper. Gupta fitted his models against a large compilation of supernova data, and he tabulated the goodness of fit for each. The standard model scores 745. His hybrid scores 746, which is essentially identical. That is his headline. But pure tired light, with no expansion at all, scores 2,580. That is not a close second. That is a catastrophic failure, and it appears in the table of the paper that is cited as evidence for tired light. He also concedes in the text that neither of his tired light models can explain the extreme uniformity of the cosmic microwave background. And in February of this year, a group at the Purple Mountain Observatory in China tested the hybrid model against a completely independent kind of data. 32 measurements of the expansion rate at different times, derived from the aging of stellar populations rather than from supernovae. The model failed by a very wide margin, but the specific way it failed is more interesting than the size of the failure. The model has a free parameter, and when you fit it to expansion rate data, you get plus 13. When you fit it to supernova data, you get minus 47, opposite signs. The model cannot describe both datasets with the same universe. I want to point out that this is a civil disagreement, not a war. Gupta has replied, arguing that a correction closes the gap, and the Chinese team thank him by name in their acknowledgements for helpful discussions. That is what this looks like when it works. But the two knockouts against tired light in general have nothing to do with any of that, and they are worth knowing because they are beautiful. The first is the shape of the oldest light. A satellite measured the spectrum of the cosmic microwave background and found it matches a perfect blackbody, the theoretical curve for radiation in thermal equilibrium, to within 50 parts per million of the peak. 50 parts per million. There is no known way to produce a spectrum that perfect except by having the radiation sit in a hot, dense, opaque environment long enough to thermalize, and any mechanism that steals energy from photons in flight must interact with them, and any interaction leaves a mark on the spectrum. Nothing does. The second is that we have watched distant clocks run slow. If the universe expands, an event happening far away should appear stretched out in time by the same factor. Its light is stretched in wavelength. A supernova at the right distance should take twice as long to rise and fade as an identical one nearby. So somebody checked. In 2024, a survey stacked the light curves of 1,504 exploding stars across a wide range of distances and measured the stretching factor. The prediction from expansion is exactly 1. The measurement came out at 1.003 plus or minus 5 thousandths, and it works on entirely different objects. A separate study monitored 190 quasars for 2 decades and measured how their variability slowed with distance. When the universe was about 1 billion years old, their clocks appear to run roughly 5 times slower than ours. In a tired light universe, none of that happens. Light gets redder, but nothing gets slower, because there is no expansion to stretch the interval between events. The observation is not subtle, and it is not model-dependent, and it is why tired light has been dead for a long time. The third claim deserves more respect than the other two, and I want to give it properly. There is a modification of gravity called MOND, which proposes that gravity behaves differently at very low accelerations, and that dark matter is therefore unnecessary. In 1998, 24 years before any of this, a physicist named Robert Sanders published the prediction that under MOND, objects of galaxy mass would be the first structures to form by a redshift of around 10, and that larger structure would develop rapidly afterward. That is a genuine prior prediction, made in print, of roughly the thing that was later observed. You do not get to wave that away, and I am not going to. But the honest accounting has to include the other side of the ledger, and the most prominent advocate of the idea has written it himself. Stacey McGaw, who has argued this case for decades, states plainly that 2 objections hold water: the residual missing mass in clusters of galaxies and the third peak of the cosmic microwave background. Both are worth understanding. On the microwave background, McGaw in 1999 correctly predicted in advance the ratio of the first 2 acoustic peaks using a model with no cold dark matter. That is a real success, and it should be acknowledged, but the same model predicted a third peak far lower than what was subsequently measured, and that is MOND's clearest empirical failure. On clusters, MOND still leaves roughly a factor of 2 of unexplained mass, and the standard repair is to add a population of heavy sterile neutrinos with about the same density as the dark matter it was supposed to replace, which is a peculiar position to end up in. The theory whose selling point is that dark matter does not exist requires dark matter at the 2 largest scales we can measure. So where does all this leave us? Every alternative to the standard picture that has been offered fails on data that has nothing to do with early galaxies. And the early galaxy problem itself, as we have spent 2 hours establishing, is not even primarily a problem about cosmology. Which brings us finally to the question in the title, because I promised you a plain answer, and there is one. Part 13, what we were actually wrong about. Have we been wrong about the Big Bang? Yes, but not in the way the sentence sounds, and the difference between the 2 meanings is the whole of what I have to give you tonight. Let me settle the version that is not true first, and then we can spend the rest of our time on the version that is. 4 separate lines of evidence established that the universe began hot, dense, and expanding. Not 4 versions of one argument. 4 measurements made with 4 unrelated kinds of instrument, sensitive to 4 different epochs, which have no reason to agree with each other and do. The first is expansion itself. There is a famous disagreement here. The value measured from the oldest light comes out around 67.5 kilometers per second per megaparsec. and the value measured by climbing the distance ladder in the nearby universe comes out around 73. The two do not overlap, at about 5 standard deviations, and resolving that is one of the live problems in the field. But look at what the disagreement is about. It is a dispute over roughly 8%, between two precise measurements of the rate. There is no party to that argument who thinks the expansion is not happening. The second is the shape of the oldest light, that black body, matched to within 50 parts per million, at a temperature of 2.72548 Kelvin. I mentioned that number 90 minutes ago and said it would come back. Here is why it matters. That spectrum is what radiation looks like after it has been in thermal equilibrium with matter. It is a fingerprint of a hot, dense, opaque past. There is no other way we know of to make one. The third is the chemistry of the first 3 minutes. In the earlier seconds, the universe was hot enough to fuse nuclei, and the theory predicts precisely how much hydrogen, helium, deuterium and lithium should have come out, given one free parameter, the density of ordinary matter. Measure the primordial deuterium in gas clouds that have never been inside a star, and you get a number. Independently, measure the density of ordinary matter from the pattern of ripples in the microwave background, a completely different physical process, at a completely different time, using a completely different instrument. The two agree to about 1%. That is worth stopping on. Nuclear physics at 1 second after the beginning, and photon physics at 380,000 years after it, arrive at the same number for how much ordinary matter exists. The review board that assesses these things puts it in words I find hard to improve on. Using only well-established microphysics, we can extrapolate back to 1 second and predict light element abundances spanning 9 orders of magnitude, in approximate agreement with observation. There is an honest asterisk. The predicted amount of primordial lithium is about 3 times what we measure in old stars, and that discrepancy has been sitting there unresolved for decades. The leading explanation is that lithium is fragile and gets destroyed inside the very stars we use to measure it, and a survey of over 100,000 stars has found evidence supporting exactly that. But it is not closed, and I am not going to pretend it is. The fourth is a sound wave. Before the universe became transparent, pressure waves rippled through the hot plasma, and when it went transparent, those waves froze in place at a characteristic size. That size is still imprinted on the distribution of galaxies today, and a survey has now measured it across more than 14 million galaxies and quasars. Here is the part that matters. The ruler exists because recombination happened. In a universe that never went through a hot, dense, transparent transition, there is no reason for a preferred scale at all. It would simply not be there, and it is there. So no, the Big Bang is not overturned. The universe is not 26.7 billion years old, and no galaxy has ever been shown to be older than the cosmos containing it. Not one, not ever. There is exactly one peer-reviewed paper that claims otherwise, and it obtained that claim by explicitly removing the assumption that a galaxy cannot be older than the universe. The authors said so in the paper, in as many words. They wrote that had they imposed that limit, the fits would have been much worse. And the lead author of that paper published a revised analysis this year, with better data, in which the ages come out at around 600 million years, close to the age of the universe at that epoch, and not exceeding it. This has happened before, incidentally, much closer to home. There is a star about 200 light-years away, sometimes called the Methuselah star, whose age was estimated in the year 2000 at around 16 billion years. Comfortably older than the universe, it made headlines. Successive measurements have put it at 14.5, then 12, then 14.2, each with its own uncertainty, and the honest summary today is that it is somewhere between about 12 and 14 billion years old, depending on method, and consistent with the age of the universe once you account for error bars. Every single time something has appeared older than the universe, the resolution has been in the measurement, never in the cosmos. So what were we wrong about? We were wrong about the beginning of structure, not the beginning of time. Galaxies assembled faster, denser and earlier than a model that has otherwise worked beautifully says they should have, and we do not know why. That is real, it is unresolved, and it got harder in January rather than easier, and underneath that we were wrong about something quieter, which is the thing I actually want to leave you with. We have never weighed a galaxy. I told you that in the first 10 minutes, and it probably sounded like a rhetorical flourish. It is not. It is the flat operational truth of the discipline. Every mass in every catalogue is light, multiplied by a recipe, and that recipe is a single power law that a physicist fitted to the stars in his own neighbourhood in 1955 over a mass range of about 4/10 to 10 times the Sun from a sample he could count with the instruments of the day. It was good work. It was never meant to be a law of nature. We took it to the edge of the observable universe because there was nothing else to take. And then, 71 years later, somebody finally went and measured it somewhere else. 31 hours of a $10 billion telescope pointed at 9 quiet old galaxies, looking for a shallow dip in a continuum produced by stars too faint to see. The stars doing the shining are not the stars doing the weighing, and for the first time we weighed them anyway. The answer came back 3 to 4 times heavier than we had assumed. So here is the shape of it. The universe was never the uncertain thing in this story. The universe has been sitting there the whole time, radiating a black body accurate to 50 parts per million, holding a deuterium abundance set in the first second that still agrees with a photon measurement taken 400,000 years later, carrying a frozen sound wave across 14 million galaxies. The thing that was wobbling was never the ground. It was the instrument. It was us. And I find that, in the end, enormously reassuring, because an uncertainty about our own methods is the kind of uncertainty you can close. You just have to go and look, which is exactly what is about to happen. In 4 weeks, on the 30th of August, a telescope called the Nancy Grace Roman Space Telescope is scheduled to launch from Kennedy Space Center, 8 months ahead of schedule, which almost never happens. It has a mirror the same size as Hubble's and a field of view about 100 times larger, and its main survey will cover more than 12% of the entire sky. Remember that the whole impossibly early galaxy problem currently rests on patches of sky measured in tens of square arc minutes. Boylan-Kolchin's fourth escape hatch, that the small volumes surveyed so far might simply be unrepresentative, becomes directly testable the moment that instrument opens its eye. A European telescope called Euclid is already surveying and already delivering. The 31 new distant quasars I mentioned earlier came from it, and its first substantial data release is due in November. In Chile, an observatory with the largest digital camera ever built began a 10-year survey of the entire southern sky this summer, imaging it over and over, which will let us watch distant clocks tick by the tens of thousands. And at the end of the decade, on a mountain in the Atacama, a telescope with a mirror 39 meters across will open. None of those instruments was built to settle this argument. All of them will. So the next time you meet that sentence, the one about galaxies older than the universe, you will know what is actually underneath it. Not a cover-up, not a broken cosmos, a chain of careful inferences, most of them sound, one of them resting on an assumption from 1955, and a community of people currently engaged in the difficult work of checking their own favourite escape route and reporting, honestly, that it did not hold. We have been wrong about the Big Bang. We were wrong about how quickly it could build things, and we were wrong about how confidently we could convert light into mass. The beginning itself is exactly where we left it, and most of what everything out there is made of is still sitting in stars too faint to see, in numbers we have only just started to count.